Hello dear listeners, I am Dr. Geraldina Fernandez, Assistant Professor of Mathematics, Department of Science, the Bhopal School of Social Sciences. In this module, we will be studying about what is successive differentiation. Successive differentiation is widely used in the expansion of functions in series and in formation of differential equations. So let's have an overview of today's module. In today's module, we will first study about successive differentiation, the various types of notations that we use to denote successive differentiation, and at the end, we will solve some practical problems related to successive differentiation. So let's start today's lecture. So now, let's look at the definition of successive differentiation. So successive differentiation is a process of differentiating a given function successively n times to find the derivative of higher orders. So this process is called as successive differentiation, and the results that are obtained by differentiation are called as successive derivatives. The higher order differential coefficients are of utmost importance in scientific and engineering applications. So if we have a function y is a function of x, then the derivative of y with respect to x is denoted by dy over dx, or it can be denoted by dy, or it can be denoted by f dash x or y1. Now this is the first order derivative of y with respect to x, where d stands for d over dx. So if this dy by dx can be differentiated once again, that is, if y is a function of x, is derivable with respect to x, we can differentiate it twice, then the derivative of dy over dx with respect to x is denoted by d2y by dx square, or it can be denoted by d square y, or it can be denoted by f double dash x or y2. And this derivative is called as the second order derivative of y with respect to x. Now if this d2y by dx square can be differentiated once again, that is, if y is a function and is derivable thrice with respect to x, then the derivative of d2y by dx square is with respect to x is denoted by d cube y by dx cube, or it can be denoted by d cube y or f triple dash x or y3. And this is called as the third derivative of y with respect to x. So in the similar way, we can find the fourth, fifth and in general the nth derivative of a function y with respect to x by successively differentiating the function 4 times, 5 times or n times. Now following notations are used for successive derivations. The first derivative can be denoted by, as we have already discussed, it can be denoted by dy by dx, dy, f dash x or y1. The second derivative can be denoted by d2y by dx square, d square y, f double dash x or y2. Similarly, the third derivative can be denoted by d cube y by dx cube, or by d cube y, or by f triple dash x or by y cube. And similarly, the nth derivative can be denoted by dny of dxn, or by dny, by fnx or by yn. So now, let us solve some questions related to successive differentiation. So the first question is, if y is equal to a cos mx plus b sin mx, then prove that d2y by dx square plus my is equal to 0. So we will start with, we will assume this as equation number 1. So let y is equal to a cos mx plus b sin mx. Now it is mentioned clearly in the question that you have to differentiate it 2 times. So differentiating equation number 1 with respect to x, we have to differentiate it twice. So differentiating equation 1, so the first order derivative is denoted by dy over dx, that is equal to a is a constant, differentiation of cos is minus m sin mx plus differentiation of sine is cos, and here we will have mx also. So differentiation of sine mx will be m cos mx. So we can rewrite it as dy over dx is equal to minus a m sin mx plus b m cos mx. So differentiating it again with respect to x, differentiating with respect to x, this time we will get difference, since dy by dx is a function of x, so we can differentiate it one more time, so that will be d2y by dx square is equal to, here minus am is a constant and differentiation of sine mx, and similarly we have to differentiate cos mx since these are 2 functions of x. So differentiation of sine mx will be one more m, we will have m cos mx by chain rule, and plus bm is the constant, and differentiation of cos will give us minus m sin mx. As you can note it down that since differentiation of sin x is cos x and the differentiation of cos x is minus sin x. So here this we are having a negative sign, and here also we are having a negative sign, so we can take minus m square common from first and as well as the second term. Here we will multiply m into m, so we will get m square. So there is one correction in the question, that here you will have m square y. So the question is, if y is equal to a cos mx plus b sin mx, then you have to prove that, then you have to show that d2y by dx square plus m square y is equal to 0. So here we have the equation 1, we have differentiated it once, we got minus am sin mx plus b m cos mx. So now we have differentiated it once again, and this time we are getting the derivative is d2y by dx square minus of am, and m into m will become m square cos mx, plus minus will become minus bm square sin mx. So this is equal to, so here we will have d2y by dx square, this is equal to minus am square cos mx we will have, then this plus and minus we will have, plus minus will become minus, and here we will have minus bm square sin mx. So what we can do, we can take negative sign common as well as we can take m square also common. So here we have 2 things, you have a negative sign in common and we have m square also in common with 2 terms. So d2y by dx square is equal to minus of m square, we can take common, and then we will have a cos mx plus b sin mx. Now children, you can see that the expression that is written within the bracket is nothing but equation number 1. So equation number 1 was this, a cos mx plus b sin mx. So the square bracket is having exactly the same expression, that is we have assumed as 1, that is we have assumed as y. So here we will get d2y by dx square is equal to minus m square y, and we can shift this m square y to the left hand side. So finally we will have d2y by dx square plus m square y is equal to 0. So therefore if y is a function of, if y is equal to a cos mx plus b sin mx, then we can prove that d2y by dx square plus m square y is equals to 0. So now the second question is, if y is equal to e raised to the power minus a sin inverse x, then we have to prove that, then we have to show that 1 minus x square into y2 minus xy1 is equal to a square y. This we have to prove. And the given equation is, we will assume y is equal to e raised to the power minus a sin inverse x. This is our equation number 1. Now you can clearly see that in the statement they are asking you to find y2 and y1. That means we have to differentiate this equation number 1, which is y is equal to e raised to the power minus a sin inverse x twice. So we have to differentiate it twice. So we will start differentiating equation number 1 with respect to x. So differentiating equation 1 with respect to x, we will get y can be written as, we can also write it as y1 is equal to, now differentiation of an exponential function. Differentiation of an exponential function is e raised to the power x is equal to, e raised to the power ax is equal to a e raised to the power ax. So in the similar pattern, we will differentiate this function. So e raised to the power minus a sin inverse x will remain as it is, multiplied by differentiation of minus of a sin inverse x. So here y1 will be equal to e raised to the power minus a sin inverse x multiplied by minus a can be taken out for calculation, and differentiation of sin inverse x, differentiation of sin inverse x is equal to 1 upon square root 1 minus x square. So this is the formula. So minus a we have taken out. Now the differentiation of sin inverse x will be square root of 1 minus x square. So we will rewrite it once again. So here we will have y1 is equal to minus a e raised to the power minus a sin inverse x into square root of 1 minus x square. So in the next step, what we will do, we will shift this square root part to the left hand side. So this will become y1 into square root of 1 minus x square is equal to minus a e raised to the power minus a sin inverse x. Now from equation number 1, we can substitute the value of e raised to the power minus a sin inverse x. We can substitute this value, replace this with y from equation number 1. So finally we will have y1 square root of 1 minus x square is equal to minus ay. And before using differentiation, once again, let us first square both sides. So what we have to square both sides. So on squaring we get, y1 will become y1 square, and square root of 1 minus x square, the square of this will become 1 minus x square is equal to square of a negative term will become plus a square y square. So now we will mark this as equation number 2, and then we will differentiate this with the help of product rule. So now differentiating equation number 2 with respect to x. We are differentiating equation 2 with respect to x. So in the left hand side we have product of two functions. So this can be taken as the first function, and the second 1 minus x square can be taken as the second function. So first function as it is, we will differentiate the second, and differentiation of 1 will become 0, differentiation of x square is 2x, plus the second function will remain as it is, differentiation of first. So differentiation of y1 square is 2y1 multiplied by differentiation of y1 will become y2, and that is equal to a square is a constant, and differentiation of y square will become 2y, and by chain rule differentiation of y will become y1. So from left and right side we can take 2y1 common. both from left and right hand side. So we can first simplify this and then we will take common and cancel it with the right hand side part. So this can be written as minus 2x y1 square plus 2 into y1 into y2 into 1 minus x square is equal to 2a square y1. So you can clearly see that from both the sides we have 2y1 as a common term. So we can take that common and cancel it. So 2y1 we have taken common. Now we have minus of x y1 plus 2 and y1 are already out. So we have y2 into 1 minus x square bracket close is equal to 2a square y1. So from both the sides we can cancel 2y1, 2 and y1 are cancelled. So we are left with xy minus of xy1. We have minus of xy1 plus y2 into 1 minus x square, and that is equal to a square y. So we can rearrange them, and we will have, or this can be written as y2 into 1 minus x square, interchange the positions of the first and the second term, minus of x y1, and also we can shift this right hand part term to the left hand side. So minus a square y is equal to 0, hence proved. So now the third and the last question of today's module is, if y is equal to a cos log x plus b sin log x, then we have to prove that x square y2 plus x y1 plus y is equal to 0. So let y is equal to a cos log x plus b sin log x. We will mark this as equation number 1 and differentiate it with respect to x. So while differentiating, we can write different types of notations. Here, as we have already mentioned in the question, that they are asking you to find x square y2 plus x y1. That means we will have to write here y1, since the differentiation of y is y1, and differentiation of cos will be minus a sin log x, and by chain rule the differentiation of log x will be 1 upon x, plus b is a constant. Differentiation of sin is again cos log x multiplied by chain rule, differentiation of log x will be 1 upon x. So here we have, or we can write y1 is equal to minus a by x into sin log x plus b by x cos log x. So here what we can do, we can take 1 upon x common and shift it to the left hand side. So next we have y1 is equal to, what we will do, we will take 1 upon x common. So 1 upon x is taken common, and here we have minus a sin log x minus a, we have sin log x plus b cos log x. Now we can mark this as equation number 2. So now we will shift this x to the left hand side. So we will have, or this can be written as xy1 is equal to minus a sin log x plus b cos log x. So now we will mark this as equation number 2 and differentiate equation number 2 with respect to x. So differentiating equation number 2 with respect to x, we get, here we will have to use product rule because x into y1, y1 is also a function of x. So we have two functions of x. So using product rule, the first function is kept as it is and differentiation of y1 is y2, plus second function is kept as it is and differentiation of x will become 1. That is equal to, again Here minus a is a constant. Differentiation of sign is cos of log x into chain rule. So differentiation of log x will become 1 upon x plus b is a constant. Differentiation of cos is minus sine. So here we will have minus sine log x multiplied by its chain rule, and differentiation of log x will become 1 upon x. So here we will have x y2 plus y1 is equal to, now you can see that we are having a negative sign in common, and what else, 1 upon x is also common. So here we can take minus 1 upon x as common. So we are left with a cos log x plus b sin log x. Now the expression that is written in the square bracket is exactly the same as we have assumed in equation number 1. So you can have a look at equation number 1. Equation number 1 is y is equal to a cos log x plus b sin log x. So this is exactly same as in our last step. So we can replace this from equation number 1. From equation 1 we can replace this whole square bracket. So we will have x y2 plus y1 is equal to, from equation number 1 we will have minus 1 upon x into y. So next step is we will shift this 1 upon x to the left hand side. So that will get multiplied, x into xy2 plus y1 is equal to minus y. So multiply x within the bracket, so or we will have x square y2 plus x y1 and shift this minus y to the left hand side. So hence proved. In the question they have asked you to prove x square y2 plus x y1 plus y is 0, and this is exactly same, x square y2 plus x y1 plus y is equals to 0. So with this we come to the end of today's session. I hope this session will be beneficial for you all. In the next session we will be discussing about the nth derivatives of some standard functions. So thanks for watching. Thank you.